So now let's look into the interference using multiple slits. So now this idea is basically inspired from the YDSE experiment, which initially consisted of two slits. Now we'll extend this idea of two slits to n slits. Now as we can see in this figure that uh, there are n slits, and let's say the ray or wave originating from the first slit has a total length of r1. So Ri denotes the length of the ith wave coming from the ith slit. So Rn represents the length of the wave coming from the nth slit. Capital D represents the distance between the slit and the screen, the usual convention of IDSC. So now, during the derivation of the required results, we will be using phasor analysis, complex numbers, and some basic trigonometry to derive the results. So, so from YDSE only, from YDSE, we are using this far field assumption that the slits are quite far away from the screen, right? So the distance between the slits is negligible as compared to the distance between the slit and the screen. The total distance can be written as n minus 1 times small d. Small d is the distance between two slits. So this is small d, and capital T is the distance between the slit and the screen. So this is an approximation which we are going to use. Now why this approximation helps is because due to this approximation we can consider these rays to be parallel to each other. These rays are parallel, and due to this condition we can easily calculate the path difference, which will in turn help us to calculate the phase difference. If it would not be parallel, then it would be difficult for us to calculate the path difference, but in this case we can clearly look from the triangles that the path difference is d sine theta, the usual YDSC result. Again there is a path difference of d sine theta, and again there is a path difference of d sine theta, and then this continues for n waves. This will continue, and this will all add up to get the path difference between the first one and the last one. Let's call this the nth one. So now what we will do is that we can write the equation of the waves originating from the first, second, and so on till from the nth slit. We can write the equation. Let's say the ray originating from the first one we can write with an amplitude of a. An amplitude of a we can write a sine omega t. From the second one there is some sort of path difference, and consequently we can write that they will have a phase difference. Then again from the slit 3 we can write a sine omega t plus 2 phi, and so on. We can write this up to the nth slit, and we can observe that it could be written as omega t plus n minus 1 phi. These are all the equation of waves originating from the respective slits. So we have assumed that they have an amplitude of a. Now to calculate the resultant amplitude, we have to use phasor analysis. So what we'll doing, we will be using, this is a kind of vector addition only, which we call the phasor addition. So they are having some respective phase difference, right? And we can calculate this phase difference from this relation, which is a quite common relation, right? That is how we'll be calculating the phase difference. So each adjacent wave will have a phase difference of phi. Again there is a phase difference of phi, then again there is a phase difference of phi. We'll use phasor addition to calculate the net phase difference and the net resultant amplitude, which is this big arrow which has the resultant amplitude. So this angle, this whole angle, this angle could be written as n times phi. If there are, let's say this is the first one, second one, and so on, then the nth one we can write it as n times phi. From simple geometry we can observe this. Let's call this is R, 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 and R. Now we'll observe two triangles. If we observe this triangle with n phi, small r and small r, we can write that this, let's say this is r by 2, this is r by 2. We can write that r by 2, r is the resultant amplitude, capital R, small r times sine of n phi over 2. We can write this. Observing this triangle in which everyone has this angle of phi, we can write that a by 2 is small r times sine of phi by 2. We can write this. So we have these two equations. From these two equations, uh, we'll be eliminating small r by dividing equation 1 by equation 2. We can write capital R by small a as sine n phi by 2 upon sine phi by 2, and so we can give the resultant amplitude R as small a times sine n phi by 2 over sine phi by 2. Now we already know that, okay, so now we already know that intensity is directly proportional to amplitude square. So we can say that IR is directly proportional to R square, and let's assume that I naught is proportional to A square. So we can say that from these relations that IR over I naught can be written as sine n phi over 2 over sine phi over 2 whole square. So we can write IR as I naught sine n phi by 2 over sine phi by 2 whole squared. Now this is the result of IR. Now if in this result we substitute n equals 2, then we will get the result which is of the usual YDSC result, that IR is 4I naught cos square phi by 2, and this result is for any general n number of slits, right? Now as we have calculated the resultant intensity, we can also get the resultant wave equation. So now we can find the resultant wave equation, and we will be using the concept of complex numbers. So just for our knowledge, we know that e to the power I omega t from Euler form of complex numbers, we can write it as cos omega t plus iota sin omega t. And we can also write that imaginary part of e to the power I omega t is sin omega t, and we can write as real part of e to the power I omega t is cos omega t. So now we will be adding the individual waves which we have calculated earlier. Yes, so these are all the waves. We'll be adding all these waves to get the resultant wave equation, right? So basically what we are doing is we'll be doing the summation of all the yi's as I varies from 1 to n. So get, let's say, the y resultant. So we can write that y is equals to a sin omega t plus sin omega t plus uh, phi plus sine omega t plus 2 phi, and so on. It continues till time omega t plus n minus 1 phi. So this can be written as the resultant wave equation. So as said earlier, we can compress this equation in terms of complex numbers. We can write imaginary part of e to the power I omega t times 1 plus e to the power I phi, e to the power I 2 phi, and e to the power I n minus 1 phi. Now that is how we are going to write this equation. Now we will use the sum of geometric progression formula, and we can write as e to the power I omega t 1 minus e to the power I n phi over 1 minus e to the power iota phi. So we have quite simplified the equation. Now we can break it further. It as a times imaginary part of e to the power I omega t 1 minus e to the power iota n phi by 2 times e to the power iota n phi by 2 divided by e to the power 1 minus e to the power iota phi by 2 times e to the power iota phi by 2, and so we'll see why we are doing why we are over complicating this stuff. So we'll take now we will take e to the power iota n phi over 2 common, and e to the power iota phi by 2 from here, and we can write this equation as e to the power iota n phi by 2 minus e to the power iota minus iota n phi by 2 over e to the power iota phi by 2 minus e to the power minus iota phi by 2. So just a small modification. Now we can write this equation as imaginary part of e to the power iota omega t plus n minus 1 phi by 2 sine n phi by 2 over sine phi by 2, right? Because the addition of these two Euler forms will yield us sine n phi by 2, and the addition of these two Euler forms will yield us sine phi by 2. So now we already know that the imaginary part of this expression, right? We can write it as that y is equals to a times sine n phi by 2 upon sine phi by 2 times the imaginary part of this quantity, which is sine omega t plus n minus 1 phi by 2. So this is the resultant wave equation, and also we have benefited by deriving this because this expression we can compare it with, right, like any general wave equation. This is the resultant amplitude, which we derived earlier also. Earlier we derived it by using simple trigonometry. This time we use complex numbers, but the benefit is that we also got the resultant wave equation by using complex numbers. That is what we have benefited from. Now we can clearly observe that, you know, for any n slits or 2 slits, 3 slits, like if it is symmetrically placed, then always and always at the center of the screen, there will be no path difference due to symmetry. Yes, the path difference will cancel out. So we can say, like, let's check that the resultant amplitude which we calculated earlier, which is I naught sine n phi by 2 upon sine phi over 2 whole square. So what we can check is this I naught can be written as a square, and we can check that what happens when we keep this expression as it is and we'll limit as phi tends to 0, right? So when we do this, we can write that sine square n phi by 2 can be approximated as n square phi square over 4 for small angles, as phi is tending to 0, so we can use this approximation. And sine square phi over 2 can be also approximated as phi square over 4, and upon further simplification we'll get IRS I naught times n squared. This is the maximum intensity which is at the center of the screen, right? Now we will try to find the location of secondary minimas, right? We have find one of the maximas, right? We have till now we have not found all the maximas, but we have found the secondary maxima, right? Now let's find the location of secondary minimas. So to find the location of secondary minimas, what we can do is we can set IR to 0, right? So now IR has 0 values when sine square n phi over 2 is 0, but the denominator should not be there, right? There should be a condition that sine pi by 2 should not be 0, or there will be division by 0, so on, right? So basically this implies that n phi by 2 is an integral multiple of pi. Let's call that as m pi. We can write phi as 2m pi over n, but again, like, this is a general solution of this equation, but we have to take care that this is not 0. So we can write from this and this conditions that phi is 2m pi by n, excluding when phi is 0, 2 pi, 4 pi, or any such pi where the denominator becomes 0, right? We cannot avoid that. Now to find the location of the secondary maximas. Now the thing secondary maxima actually did not exist in the YDSC experiment, but it will exist in this n slits experiment. So what will happen is that in YDSC there was a constant level of peak, right? This is what had happened in YDSC. But when we are saying about n slits, there will be some low height peaks and there will be some high peaks, right? So this is what we call the secondary maxima. This is the secondary maxima, and the condition which we'll use to derive the secondary maxima is we can differentiate and set the derivative of the intensity to be 0, right? And so let's analyze how we will find secondary maxima. It's a quite complicated process. So there are small bumps in the graph which I just showed as what we call the secondary maxima. What we generally do is we set the derivative with respect to phi as 0, right? And if we get the location of secondary maxima, and also we can write that the second derivative of IR with respect to the phi, this should be negative, right? For a maxima this should be negative. So upon looking and investigating onto these conditions, we generally derive onto the conclusion that n tan phi by 2. I'm not going into the derivation of this, but I'm telling the result of these two. conditions, which is n tan phi by 2 is equal to tan of n phi over 2. Now the equation has to be solved numerically. However, for large n, the solutions of phi are generally very close to the odd multiples of pi by n, excluding the values of where phi is 2 pi and plus minus pi by n, right? Because these values will be lying well within the primary maxima region. So basically the odd multiples of pi by n are a solution. This is what we can make the deduction are these solutions. To understand this better, let's take the case of n equals 8. Let's take the case of n equals to 8. How a graph or for further simplification we can take n equal to 4. Plotting n equal to 4, how the graph will look, you know, at the origin or at x equals 0, I have already proved that there will be a maximum, right? I max equals n square I naught, which I just derived. So let's say, this is IR by I naught on the axis and this is phi. So phi equals 0, this is the peak, right? There will be a minimum, there will be some bumps, right? Again the peak will go up, will come down, and a symmetrical situation will happen on this side also. Okay? This location is pi by 2, the location of secondary minima for n equal to 4, the plot for n equal to 4. This location is 3 pi by 4, this location is 5, this is 5 pi by 4. These are all the location of the secondary minima, secondary maximas, and this is the primary maxima regions. Now that is how we show it. Now one very important observation, like it will not be visible from this graph, but let's take the graph n equal to 8. So n equal to 8, graph looks something like this, where there will be more secondary maximas. First peak, second peak, third peak, then again, then again, then again. The height of the secondary maxima peaks is also not fixed. That is also an observation. And the same graph, right? The same graph on this side is symmetry. Now the symmetry holds from this side also, but just see this perspective, right? Here also there is a symmetry. There is a symmetry from the view of the lowest peak of the secondary maxima. Let's say these have the lowest peak of the secondary maxima and they are holding a symmetry in these directions. Now why does this happen? As I told earlier, for n equal to 2 there will be 0 secondary maximas. We do not observe any secondary maxima. For n equal to 3 there will be 1 secondary maxima. For 4 there will be 2 secondary maxima, and so on and so on. Now this is phi equal to pi. The important deduction is that the bump sizes are symmetric around phi equal to pi, or in general any multiple of phi. In this case for n equal to 8 it is phi equal to pi. In other case it will be phi equal to m pi and so on. But why does this symmetry happen? This is the question. This is a question which is a very worthy question. Like now, the basic answer of this symmetry can be sort of said uh, that there is a periodicity in the sign equation, right? There will be some sort of periodicity in the sign equation around this phi equals pi, and that is how the peaks are so symmetric about phi equal to pi. Now this is all the results of the n slits interference. Now, like there is a very genuine question, right? That what will happen as n increases? The number of slits keeps on increasing, right? Now, as the number of slits is increased, the primary maxima or the tallest peak in each class becomes narrower but remain fixed in position, right? And the number of secondary maxima keeps on increasing. As we are seeing, it keeps on increasing the secondary maxima. For any value of n, the decrease in intensity in maximum, the left and right of the central maximum, indicated by blue dashed arcs, uh, is due to the diffraction patterns from the individual slits, which can be neglected here. So, some sort of diffraction also happens, which we are neglecting while deriving these results. But it will be interesting to derive those results, that why there is a bluish tint and so on, bluish dashed arcs. So while deriving this result, we have taken coherent sources and not incoherent sources, and the far field assumption. And that is how we are deriving these results. So to basically justify these points, we can, as I already showed, that for secondary minimas, the condition was even multiple of pi by 100, excluding, as I have told earlier, phi equal to 0, 2 pi, 4 pi, and so on. So what we did is, we take, for n equal to 4, we can take e as 2, we can take e as 4. Taking e as 4 will give us pi, which is the location of secondary minimum. And about, as I have told, that around the multiples of pi there is a symmetry. Again you can see the symmetry, again we are seeing the symmetry, and the symmetry holds as we are increasing n, right? And it is due to the periodicity of the sine functions, which we have derived earlier. And also interesting thing to notice that in n equal to 8 graph, the bump size is the shortest around phi equal to pi, right? And we can logically say, right, I have told you that IR is I naught times sine of n phi by 2 over sine of phi by 2 whole square, right? So now if we increase the value of the denominator, like, it's a very subjective argument, it's a very qualitative argument, that when phi happens to be pi, the denominator is maximized, and so the intensity is minimized of the secondary maximum. So the bump will be the shortest at phi equal to pi. So this is another argument which we can use for the reduction. And we can also observe that as we get close to the main peaks, as we are getting close to the main peaks, the primary maxima regions, the bump is getting increased. So this is how we analyze the multiple slit experiments. It's a bit different from the YDSE because due to the introduction of secondary maxima. So it is a beautiful phenomenon, right? We have beautifully derived using complex numbers about the resultant intensity and what happens when n increases, right? So it is pretty easy to prove that why the peak will get narrowed as n basically increases. And any sort of problems with 3 slits or 4 slits can be solved by these methods using the path difference and phase difference, intensity relations, and the very basic methods. So that is all about the multiple slits. That is the main results of multiple slits. Thank you.